In 2019, NHS Foundation Trust provided data on 1.6 million patients to Alphabet's DeepMind without asking for permission from the patients to share their private data. Keeping in view the privacy concerns of patients, Google canceled the plan to broadcast chest X-ray scans on account of concerns of patients as they were carrying personally identifiable information. The second example is a dataset containing above 10 million images of 100,000 celebrities created by Microsoft, called MS Celeb. This has been removed since celebrities expressed their concerns that they were not even aware of being included. Besides this unconscious revealing of personal data, there is a type of personal data we are uploading on social media by ourselves. For instance, we visit a restaurant or a store and take several images of the food or product we like and post them online. Most of this data is transferred to cloud computers that have considerably enhanced the probability of tracking this personal information. The first concern is called data persistence, where data exists longer than the human subjects that created it. The images of your car photo may store for years, and you may forget its existence. The second concern is called data repurposing, which means data are being used beyond their originally imagined purpose. For example, in a decade's time, parking habits may be part of the data used by grocery retailers to analyze an individual's preference for shopping. Finally, the concern called data spillovers is associated with the case when data are collected on people who are not the target of data collection. The photo may record other people and they may be identifiable through facial recognition, or incidentally captured cars may be identifiable through license plate databases. As concerns grow, many privacy-preserving techniques can largely conceal the identity of persons or groups, are now a standard staple in AI systems. These techniques must balance the need for privacy and the usability of the system. We first discussed the technology that is called differential privacy. Before trying to understand this method, let us consider this example. Assume your parent is trying to get the score of your final exam this semester, but your teacher is trying to keep the privacy of the students. The only information your parent can receive is the average, median, and some other general information about the scores. In this way, your parent learns some information about the final, but your own privacy is preserved. This is the idea used by differential privacy. The information requester will not be able to be 100% sure to infer any specific individual. But please note this protection is offered by the number of students in your class. If the class contains 100 people, each person's score contributes just 1%. However, if the class contains scores from only a single person, that person's individual data contributes to 100% of the class data. The key insight of differential privacy is that as the query is made on the data of fewer and fewer people, more noise needs to be added to the result to produce the same amount of privacy. In this example, if your parent asks the average score of students with your last name, to protect your privacy, your teacher must add some noise in the result. Otherwise, your scores will likely be identified. Though this partially solves the problem, individuals are not identified, but the data we uploaded to the server may suffer from data persistence and spillover. A solution to this problem is to encrypt the data. Encryption is the process of encoding information. This process converts the original representation of the information, known as plain text, into an alternative form known as ciphertext. Ideally, only authorized parties can decipher a ciphertext back to plaintext and access the original information. However, this stops us from utilizing any service provided by the system. The privacy is preserved, but we again receive nothing helpful. Scientists then try to find a way to encrypt the data, yet still allow computation. This is termed homomorphic encryption. It permits users to perform computations on its encrypted data without first decrypting it. These computations are left in an encrypted form. When decrypted, the result is identical to that produced had the operations been performed on the unencrypted data. Homomorphic refers to a specific correspondence, and in this context, it means the calculation on encrypted data is the same when it is being decrypted. For example, let's consider the easiest encryption, called the Caesar cipher, which replaces a letter with another letter with a fixed number of positions down the alphabet. For example, with a shift of 3, A will be replaced by D, and B will be replaced by E. Letter Z will be replaced by C. Consider our calculation is to concatenate two words. The encrypted words are uploaded into some remote computer for this computation, and the result is transmitted back. We then decipher the result and find this is just the result if we conduct the same operation with the plain text. But the good thing is the remote computer cannot tell what is being transmitted. In this way, both privacy and utility are preserved.